Shweta,
Start.
you can start.
Good evening to all. I feel immense pleasure to extend a warm welcome to all present here for the seminar on the topic Ocean Observation. Now, I invite Dr. S. Brinda, IEEE Counselor, to give the welcome address. Please, ma'am.
Sir, wait. We have to check the inform, sir.
Okay.
I'm online, ma'am.
Yes, sir. Shall we start, sir?
Yeah.
Yeah, okay. Good evening, all. On behalf of Department of ECE and on behalf of Sairam IEEE, I take immense pleasure in welcoming all for this evening seminar. And there is after long period, we are kickstarting all the events, all because of the conference work we are held up with that is the IEEE IC3 IoT conference work. So after that, we are starting the events. Today is the first event in this semester for under Photonic Society banner. And a few staff members and students requested me to initiate some events based on ocean observations, so oceanic related research work. So that's why we thought of inviting sir. So Tata Sudhakar sir is closely associated with the Sairam long period through IEEE forum. And today sir is joining with us for IEEE forum also. So we are very happy to welcome you, sir.
I'm actually IEEE OES Vice Chair in Chennai, ma'am.
Yes, sir. Yes, sir. But for talk and other activities today, I came to know. Okay, sir. Thank you, sir. And so we thought sir is the right person to talk about the research opportunities and product, what type of projects we can take up in oceanic side. Sir is the right person, so we invited him, and along with you all, I'm also very much interested to listen sir's talk. So we are happy to welcome you, sir. Over to you, sir.
Yeah, thank you, ma'am. Can I upload my presentation?
Yes, sir.
Yeah. You can see, ma'am.
Yes, sir. Visible, sir. But in your there is profile. So you didn't mention that role, sir, Vice Chairman. That's why you're not aware.
Yeah. So, but anyway.
Only have mentioned scientist G.
Yeah. Actually, profile, there are so many things. So
many things. So, we missed it.
You can see my screen?
Yes, sir.
Yeah, okay. Good evening, all of you. All of you must have tired after the full day college and then must have reached home. So I was trying to make it very light. And then on this topic, I remember coming to Sairam College and then talking about it mostly on tsunami warning system. Now I thought I'll put up something which is a little bit different. I was actually working from morning on this so that I will give you, like Madam was talking, opportunities available. The two things are happening in the country. Government is actually pushing very hard for doing the Make in India. And we are also going to start a incubation center in NIOT. So there will be opportunities for the colleges and other people to do work which is required for NIOT. So I thought I'll put up something little different from what we used to, what I was normally used to present. Let's see how it goes. So the standard is Earth 71% water. So oceans are very, very important. They are actually rich in a lot of minerals, which we are yet to exploit. Except for the crude oil, I think we are not touched anything. And it's also very, very important for the climate because the energy actually which is coming from the sun, which is getting transferred through oceans. So it is very important to study the oceans, and then we'll see why actually oceans are still a mystery. Probably we know more about moon or and Mars, but we hardly know what is actually beneath our ocean. And then they play a very important role for the climate study. So when we're talking about observation, what are the properties of we need to measure? Temperature, salinity, currents, sea level, surfaces. There is actually list is very, very big. We will actually cover some of the things, and then we will see what are the technologies are used for doing these measurements, because the list is very, very big. So I will actually have only few technologies which I will go in detail, and then some of the things I will mention what are the things which are required actually to do that. Because see, there are the list is quite big. So what are the challenges we have? Oceans belong to us, so we it's actually very difficult to do the measurements in the ocean. So there are a lot of constraints out there, especially when it comes to technologies. So we will go through actually what are the constraints are there in the measurements also. So we can actually break it, do this measurement into three different categories: physical, biological, and chemical. If you do physical, we are doing actually sea level. That's a tideless. And then we have actually data boys which actually do a lot of measurements. We will go through that. And then these are the technologies which some of them will be touching how the physical properties of the oceans are. Then I will actually come to the what are the physical properties out there. And then when it comes to biology, we have actually need to do a lot of study on the chlorophyll, which is actually primary productivity for the or most of the uh, food for the most of the sea mammals. And then the chemical, what are the chemical parameters of the waters, how they affect the atmospheric research. And then it comes to the climate. Climate, actually, if you see these lines are uh, the cyclone tracks. So if you want, they are not really uniform. So to measure or to predict this cyclones exactly, we need to do a lot of measurements in the ocean so that we will know when a new cyclone is developed in somewhere in the ocean, and then we will know the track so that we can actually make a preventive damages we cannot avoid, but it will probably we can do some sort of a preventive measures to reduce the damages. If you take the marine instrumentation, it's actually a lot of difference between the land and marine because if you take ocean equipment, they have to undergo a lot of difficult because of the pressures. Every 10 meters, you have one bar. So any equipment what we are making in the oceans, actually we need to create some sort of a casing which is capable of taking the hydrostatic pressure of the water. Uh, if we are working on about 100 meters, or then we need to have a 10 bar pressure casings, and if you go to 1,000 meters, it will be 100 bar pressure. So we in NAOT we work up to about 5 to 6,000 meters. So we do the casings up to 500 to 600 bar. When you are doing this type of things, you have to use a lot of different materials, because not all the materials are capable of managing the pressures. If you are looking at a low pressures, we use actually Delrin and some sort of FRP things for the surface to 100 meters. If you're going to below, we use aluminum. And if you're going still below, actually, of course, aluminum is a better material in the light. Then we use a stainless steel and then titanium. Now there are new cases are coming with a carbon fiber too, because carbon fiber is very light, but still it's actually a little difficult to not only make for all the conditions, so some places even carbon fiber is used. Then comes the humidity. Humidity in the coastal zone we all experience. We are from Chennai, so we know what is the humidity. A lot of water content will be there. So the whatever equipment we are making actually need to take care of this humidity issues. And there is a temperature variations are there. Temperature variations because surface water is around 28 degrees centigrade, and as it will go down, about 4,000 meters, you probably have 4 degrees centigrade. So because of this, what happens is when you enclosure, say at the surface where we have 35 degrees or 45 degrees, depending on which time of the year it is. So you have actually air with a huge humidity, which is 95%. And then you're enclosing it. Once it goes to 4 degrees, this actually gets condensed. then your water droplets will form. Once you have water droplets, it's very dangerous because it can actually short electronic circuitry. So it is very important that we take care of that humidity and temperatures. Basically, what we do is we use a nitrogen to purge remove the oxygen from the casing, so that even in case the water droplets cannot form. Then seawater has a salinity. Of course, it varies from the location to location, but salinity actually affects a lot of materials. Then you have a corrosion and biofouling. Biofouling is basically a growth because of the small life which exists in the oceans. So why biofouling is a problem is, suppose now the technology, some of the what I'm going to do is optical based instrumentation. You use different wavelengths of optics to measure some parameters of the ocean. So when the biofouling happens, actually there's going to be thin film going to form on this optical lenses. So then your calibration goes. So it's very important to we take care these two issues. Then marine is actually dynamic and medium. Then accessibility is poor, and you need a platform like a ship to do any measurements or any experiments. Then the ocean parameters numerous, that's very huge. It's a space variant. Space variant is we call it because suppose you measure the salinity of the water at 100 kilometers from Chennai, and then you do the similar measurement at 200 kilometers from Chennai, it's going to vary. So, and then time variant, it actually like some of the parameters like the chlorophyll, actually it moves up and down because of the temperature. So whether you what the measurements you are done in the daytime may not be true in the nighttime. So you need to do continuous measurement. Then interdependent. Some of the parameters are interdependent, like a salinity and temperature. We need to measure together to actually get the correct salinity at the position. So there are many parameters which are interdependent. And then time and cost are intense too. Oceanography is a very expensive hobby because then the technology, even though it looks very simple, it is one of the most rugged systems we need to make, and then and equally expensive to go into the location do the trials. So there are two type of instruments we have this observation platforms: in situ and remote. In situ is basically physically somebody is going on the ship and then do the measurements, and remote is we are using some sort of a remotely operated systems to do these measurements, like radars and microwave tide gauges and things like that. Now, of course, there are a lot of other systems are also come up like drones. We can use it. We are doing the experiment for drone. I didn't add any slides, but we are done an experiment using the drones for doing the ocean measurements. So it is a general classification of the all oceanographic instrumentation. We have in situ and the remote, and then for operation platforms, fixed, ship, buoy, submersible. We'll cover some of the things. And then remote sensing, we have systems. We are sitting on seabed, using the aircraft, satellite. Satellite actually has done a lot of work because probably most of the models are actually able to work just because of the satellites are doing a lot of measurements. But we need some sort of a the validation systems on the ground, like buoys and other systems, which actually because satellites are normally, all the satellites are under 900 to 2000 very high altitude. The remote sensing satellites are at 900 kilometers, and then if you have a geostationary satellite, which is actually 36,000 kilometers. So there's going to be a lot of errors when you're looking from the optics from that height. To correct those errors, we need to actually have some sort of a validation system on bottom. We have one system actually in Lakshadweep for the specially made for the ISRO. We call it a CalVal buoy. It's a calibration validation buoy that has actually radiometers, which is actually measuring the upward and downward radiance, all the full spectrum of the electromagnetic wave, and basically visible and infrared. That because is basically the say what satellite is looking at that position and what is the radiance at that position physically and what satellite is measuring. With that, actually, we can do the validation. One of you, if you come, I will actually show the data, how it looks. Okay. Then we can put a towers. There are HF radars we have it on the coast, which is for measuring of the waves and currents. We can use this remote technology. Then all the equipment need to have some sort of a telemetry to transmit the data to the host place. So what are the advantages and disadvantages using this thing? If you use actually intuitive with better resolution and accuracy, one difficult thing is in remote systems, we don't have sensors in for most of the parameters. So what they do is in most of the times what actually used to measurements, so the water is collected and then it is put on board to do the lot of chemical analysis, because ocean still there are many parameters which need to be technology needs to be developed for measurements. If you take a remote, do not depend on state of the medium, do not affect the parameters you measured. The accuracy may suffer. Then not suitable for all the parameters, like what I mentioned. Still, the technology is not available for most of the parameters. So when you are doing any instrumentation, what we need, your teachers may be knowing it. For the students, I thought I'll put it up this. You have a sensor. What is sensor? Basically is a instrument which converts a physical property into the electrical property. It could be temperature, pressure, anything. Temperature, what it does, the temperature, it converts into electrical signal. So then you have a processor or conditioner, because sensor basically what it does is actually very, very small voltage, either voltage or current variations it gives. So those variations we need to use actually condition it so that your A to D converter can read the data. So you have this conditioner for converting the very small variations in the sensor element to a larger required for doing the final measurements. Then we have a recorder and display, and of course a power supply. And then we need a housing, pressure casing, and which is power compensator. So basically, what we are doing is in the instrumentation is we are actually putting a one sensor to convert your physical property into electrical property, and then we are using the processor and conditioner to read that data and to do by A to D conversions or something like that, and then convert it into like if it is a temperature, you put it to degree centigrade or a Fahrenheit, readable into parameters. So when we are doing this measuring technique, it could be direct and indirect. Resolution. What is the resolution? The difference between the one value to the resolution. We call it A to D converter. If you take it, most of you are familiar with this. We have a 8-bit, which has a 256 levels it can do. If you have a 12-bit, 24-bit, up to 24-bit A to D converters are available. So 2 to the power of 12 is the least variations which are going to measure it. Then your accuracy and repeatability. Repeatability is very, very important because that's where actually we get a confidence of the measurement. Repeatability basically is, if I suppose I'm measuring the temperature at 24 degrees centigrade, 24.1 say. So tomorrow, actually, if I come back and if you do the same thing, I should be able to measure this correct temperature. So your sensor should not give it two different things. So repeatability is very, very important. And calibration is because all the materials which is going to drift. Because the sensor, what we are using is basically some sort of a material which is actually has some properties, and then it will have a drift over the years, over the period. Somehow, like I will go through some of the sensors what we put in ocean, they stay for 1 to 2 years. Actually, normally we put only for 1 year, but because of the COVID, we could not go back and then recover the buoys, some of the buoys. So the sensors are there for 2 years. So in 2 years, there is going to be some drift which is going to happen because of the because we are using so many electronic equipment. All of them will have some sort of a drift. So aging, because of the aging. So the overall drift is going to be there. Then we need to calibrate and then see to correct it when we are doing the next time the measurement, or There are actually, we do the calibration in the Argo floats where we use a reference of some other place to even to correct the whatever data which is already available. So we do pre and post, like when you are deploying, we do the calibration, and then when you recover, do the calibration, and then we actually correct the data which is already measured. Then maintenance and repair. So when you after the collection data, we need to process it, and we need to do the quality of the control we have to do, and then we have to store it in the proper format. It's very important because this data is actually climate data. Most of the observation, ocean observation data is used for the climate studies, and climate models are huge models are there. Some of them are working on very big supercomputers, and then they take the data from not only from India, and they take a whole global data they take. So when you're actually reading the data from all other sources, it has to be in one standard format. So like every location, what we are doing measurement is will have as one universal ID, but it's given by international organizations. Then if you are measuring the temperature, I'm going to say 20.1. It is not like that. If everybody is measuring that format, 24.01 or some 0.01, like that, we need to have a standard. Next 5 bits is going to be temperature. Next is some other parameters. So format has to be perfect for sharing the data with each other. Then we need to find a different modes of transmitting the data to the reception system to us. We will see some of the things. And also sharing in between the user agencies. What we do is we actually dump the data. There's something called GTS. GTS is called Global Telecommunication Services. So there is a format set for each observation. So with the ID, we will know what observation platform it is, and then it actually expecting you to add their data set. If the data set is not there, so you just put a zeros there so that the program which is reading the data understands that this data is not there. And then even if you were to say whether it is calibrated, non-calibrated, so that some of the forecasting people who don't want to use the uncalibrated data, they liably ignore it. So when you're actually sharing the data between two users or two institutions, we need to clearly tell what type of data I have, what is the quality of the data, so that the user actually has an option either to use it or not use the data. So when you look at the evolution of the marine instrumentation, they're actually earlier ones are very crude. They're actually having the self-recording and with charts with a low resolution and accuracies. Then for reading the data, we used to have a lot of human skills are very important because the data reading is from the charts, you need a lot of expertise. Today, the technology has changed. I seen last time actually, I came for one of your project, something hackathon or something like that. Most of you are using ML algorithms to do the projects. So today, actually, we are also started using it. We are using, I'm calling because individually people will be knowing a lot of tech things, but when you're trying to put it in such a huge systems, the authentication of the system is wholly very important. So we are also now the observation systems have a lot of machine learning algorithms to improve the overall functioning of the system. So the electronics has improved, which has actually improved the whole overall easiness in doing the ocean observations. And today, actually, if you see it, nobody does one measurement. We have instruments so actually we do 6 or 12 measurements together. I will show you some example of that. And then most of the systems are interlinked and connected using the IoT systems. These are the systems I'm going to talk in general. These are the Argo floats. Probably I have some sort of slides for this. These go vertically up and down the ocean to do the measurements of all the parameters. These are the mood buoys, which anchored one. Now we are allowing the students, if you people want, you can come and see physically all the systems. Drifting buoys are basically for doing the ocean circulation measurements like currents and surface SST. This XBT is a funny system. Actually, this is some sort of a disposable system. If you see this, a brown thing, what we are seeing is actually a copper wire coated. So then you fire this system, it just goes down into the ocean, and then you, as long as it goes down, you keep getting the temperature and the salinity of the thing. And then once after some time, actually it get detached with your reading system and then goes down to the water. And these are current meters. We will see some of them how it functions. This tide, tsunami, we will see the functionings. And then this is the ocean glider. This is a new way of doing the measurement. It's a similar glider what we see in the land, land in the sense of the air. It actually goes in a trapezoidal way into the ocean to do the measurements. And these are the HF radars, which are used for measurement of the surface currents and waves. For doing any measurements, GPS position is very, very important. We know latitude, longitude. We all use Google Maps for traveling. So, but let us see how GPS functions. It has actually 24 operational satellites, which are moving around 26,000 kilometers from the Earth. And these are in 3 orbits. Who uses this? Everybody in the world today uses it. Actually, the list is what we have put up is very, very small. This is not only used for the navigation of us on the land, we use it in the air, sea, even the submarines also. They will actually have some sort of a, a profiler which comes up once in a while and then collect the GPS position to correct their navigation system, which actually works on that recurring time, because submarines, they really don't come out of the water for a few days. So it is used for a lot of other applications for surveyors, surveying, and the hikers. Actually, the one of the option available in the GPS, we use something called RTK GPS, which gives even the elevation. So we use the elevation to even to do the measurements of the waves. It's a huge project done basically by controlled by Department of Defense. There are similar systems available with other countries also. Chinese have, and the European users have Albatross, and Russians have GLONASS, I think they call it. And then Indians actually call the NAVAC, I think we call it. So everybody has a navigation system of their own today. But of course, everything with GPS is probably is the mother of all the systems. So how you measure the position? It's basically a ranging system. If you see the first picture, if I'm standing anywhere in this lobe, and I get a one position from the one distance from the satellite. Satellites are actually giving their orbital position, and then whatever handset what we have is actually measures the distance of the satellite to you. So when if you suppose I get about 26,000 so many kilometers, I may be anywhere in this arc. So if I use a two satellites for my position, so probably when in intersection, I may be here or here. And if I use a 3, I will be here. And then actually there is one more position here. So the normally it's the best position what we can get is we need 4 satellites. So what is the accuracy what we have today? We can actually get up to 1 to 5 meters. There are 3 different codes are there, L1 and L2, L5. But we all use L1. The remaining 2 are used for the military, and so we call it actually survey equipment. There are actually much more accurate. They are sub 1 meter accurate equipment. So this the person is actually standing here, and then he's getting his distance from the satellites, and then the handset what he has will calculate the actual position based on these distances. These are the satellites, how they are moving it in different planes. Any given time, if you see This is the one which actually is moving it. Any given time, you will find actually 8 to 10 satellites which are visible. And if you see this picture, when it goes up, because these are all our polar satellites, when you go towards the pole up and down, actually you will find the visible satellites are more. When it comes to the equator side, it will be little less. But any given time, today you will find more than 5, 6 satellites visibility. So Indian Regional Navigation Satellite, IRNSS it's called. It is a little different from the GPS and other positioning systems what others have. We use actually few geostationary satellites and 4 polar orbiting satellites to get our position. And then these satellites, the position is actually, we are not really looking at a position accuracy beyond Arabian Sea, Bay of Bengal, and Indian Ocean. So we are not actually looking at Europe, Atlantic, or Pacific Oceans. So then we use something called DGPS because, well, like I was saying, some places we need actually accuracy in centimeters, not in meters. So what we do is actually see, we have one reference GPS system, which is fixed on some sort of a building, and then it transmits its position continuously. So it's because the satellites are very far from that, and they will have a lot of ionosphere corrections which needs to be made when it comes to your receiver. That's where that accuracy is suffering. So you are not going very far from this reference system. So with using this as a reference system, we can actually correct these ionospheric corrections and then get a accuracy up to 1 to 3 centimeters. We will see how the detail of some of the technologies what we discussed. First one, actually, I will see the tide level. Tide level is much easier. We'll see only 5 of them: tide pole, floating swell well, and pressure, acoustic, and satellite. This we would all have seen. If you go to any dams, we'll find this thing is marked on the side of the dam. That there the water level, wherever water level is there, that you see it. So this is similar, very, very old technology. The harbors, they used to have it actually painted onto the wall to see the tide value. It's inexpensive, but it's actually very, very cool. Then actually floating stilling well thing has come. There are wells available in the harbors. Then there's one, this is the floating disc, which is actually put onto the bead, and then you have a small counterweight here. So whenever the water level goes up, this goes up, and the weight pulls down, and this whole thing rotates. Because it is rotating, this also is actually moves on the chart. So you're getting a sort of a marking on the chart, that level change of level. This is actually a very robust system. It has been used by many, many years by people. Of course, the technology is also now obsolete. Then the pressure sensor has come. This is much easier. Your sensor, which actually converts the pressure into signal, it's kept here. This is the formula for the converting the measurement into the pressure to the depth. It's easy measurement, simple to install. You can just actually lower it to the water and see it. This we can do it in our water tanks also. How much is the water is there, we can see that simply. It is prone to error because there is a sedimentation, density fluctuations is going to be there because salinity is not same in the
Kindly mute yourself, students. Satya Prasanna. Sorry, sir.
It's okay. All of them are at home. Okay. So it is prone to errors because of the density variation which is going to happen in the because what we are measuring pressure is nothing but hydrostatic pressure. Then comes the acoustic tide gauge. This is a simple one. You have a small 8 kilohertz transducer which actually sending acoustic signal down, and then the reflection is measured, and then time travel is taken. we all know what is the speed of sound in the air. So with that actually you can measure the tide value level. It is prone to atmospheric disturbances. We need to do the temperature corrections because we are looking at centimeter variations. Then the technology of radar has come. That this is probably is the easiest and most accurate system. It actually works at 2.8 gigahertz. This signal, this system, and it transmits the pulses down, and then this is actually signal. So it receives a signal, and then it is very accurate. It's in millimeters. Then comes the satellites. Because why satellites are required is suppose you wanted to measure the tide in the open ocean, where because most of the technology what we spoke so far is actually they are put in the harbor. So if you there are satellite altimeters, you have some sort of a radar or signal which is transmitted from the satellite and which actually touches the water level and comes back. So you can actually measure the distance between H1 and H2, and then you can calculate the time. So this is ideally suited for the open ocean, but normally some sort of beacons are available in the closest to land, so that to do the corrections for the measurement what we are doing in that. So maybe India also has one satellite called Saral Altica to doing this measurement. So precise knowledge of the orbit is needed. Okay, this we already covered. Then comes the drifting buoys. These are used for measuring the ocean currents. This is simple system like you throw any bottle into the ocean, it keeps drifting it. Only thing is it has some sort of a transmitter, satellite transmitter, so it is giving its position. So with that, we will know actually how the ocean currents are moving. But we need to do it perfectly correct. So what it has done, it has some sort of, we call it drogue. Suppose if you want to measure the currents at 15 meters, the drogue is at 15 meters. If you wanted to measure the current at 5 meters, so it will be somewhere here. So the drogue is the one actually pushing the whole, moving because of the current. And the top one is at the surface. You have a satellite transmitter inside, and then air pressure sensor giving the barometric pressure. That's additional amount. And then you have a skin temperature. Probably this is the best equipment to find out what is the ocean skin temperature is. So this is what NIOT has come to technology and transfer to industry. And then this if you drop it, if you say we dropped here, it was actually moved like this and came back to the land. And then there's because the ocean currents actually is not uniform in all the seasons. And so we put it in same place also in a different period of the year. They actually the currents actually will take the drifter to different positions. And most of the time, what happens is even though the drifter is capable of working for more than a year, it actually beaches in somewhere in the land, and then somebody will destroy it. And some of them will come back to us because we write the address from the drifters or who was the owner of that. So this is how you see it if you drop here. So that means that ocean currents are moving this way. Then comes the Argo floats. These are basically used for measuring the subsurface parameters. This is probably one of the most innovative technologies which has come in last 20 years. This is called a neutrally buoyant floats. It has actually has I don't know whether I have the picture. Yeah, the picture. This, if you see, it actually is a small reservoir where the oil of 200 ml is there, and then you have a bladder which is outside the profiler. So what actually happens is we are going to play with the buoyancy, because if you reduce the buoyancy, the float will come up. If you if you reduce the buoyancy, float will sink, and if you increase the buoyancy, it will float will come up. So what you do is when you drop the buoy here, you actually reduce the buoyancy, so it will sink, and then it is somewhere it is at neutrally buoyant floats. At neutrally buoyant, it will actually have 1,000 meters. We know what is the density at the face, and then we fine tune the float weight there for that depth. and then it remains there, and then it actually drifts over for a few days. And then it goes up to 2000 meters when you actually start the profiler, and then it starts coming. While coming up, it actually measure all the parameters what we need. Normally, it is salinity, temperature, and reference to the depth is measured. But today, oxygen, chlorophyll, turbidity, there are actually many food sensors have come. So we are actually doing the measurements for all of them. And then once it comes up, it transmits the data to the satellite, and satellite will receive your the data and then transmit back to the Earth station. And then once that cycle is over, again it will go back into the and then sits into the ocean layer which we are tuned. These are global array of 3000 floats, even though they look very close by, but if you say take it the diameter of the Earth, they are actually quite far. So any given time, there are about 3,000 floats are profiling the oceans and giving us the data continuously. This is the temperature salinity profile velocity estimation. There's a global ocean circulation experiment program is there, where which uses this data in real time. So if you see the temperature, this is 2000 meters, actually it varies. This is the salinity, and this is the temperature. Actually, as you go down, the temperature decreases. This is a very good salinity temperature sensor we use. It's actually Seabird. It almost has a monopoly in the world. We have worked out with Chennai IIT, Madras IIT to develop one. It's in the process of actually doing the validation thing. We have developed it and give it to industry for making the 4 pieces. So sometimes down the year, 3-4 years, I think we'll have our own sensor. If you take it the ocean, these are the measurements done by one of the Argo systems. This is how the temperature actually varies in the ocean. Top is hot. As you go down, it will be cold. You can see the chart here. Like I said, the technology has gone up. We are using a lot of autonomous vehicles. This is called AUVs, autonomous underwater vehicles. Your actually colleges, we used to have a competition called SAVE, students AUV program. Now it is stopped because of, I think, COVID, the funds are stopped, and Dr. Venkatesh also is retired. So that program, I think, I don't know who's going to start it. So these are basically vehicles which can go into the ocean, do the measurements, and come back to you. There's a lot of complex technologies are involved for navigation and communication in this. These are different of systems actually, AUVs. This is the propeller, which actually moves this vehicle. And this is a GPS and antenna, because it will be, when it comes up, actually it needs to communicate to the satellite to transmit the data. And of course, this is a handle. Then we have a sensor suite here, depending on the requirement. Normally, they have a lot of other sensors like a depth altimeter to know exactly where the vehicle is. AUVs are normally not just used for the measurement of environmental parameters. It's actually used for mapping the ocean floor. Suppose you have a telephone cable. This is very common. We have one internet cable between India, Andaman and Chennai. So if you want to see what is the status of the cable, you can send the one on vehicle like this, which actually continuously maps that cable, and then it comes back, and when it comes back, you can see that what is the condition of the cable. So this is how it is. So waypoint 1 to waypoint 2, it moves, and then what it does is actually when waypoint 1 it sinks inside, and then continuously start collecting data, and then comes up and that waypoint 2, and then with the location we actually redraw the path. So we'll see what are the different kind of buoys there. These are the tsunami buoys. These are sitting on the bottom of the ocean and then continuously looking for the variations in the pressure waves difference. So once there is a tsunami comes, it sends a signal to the surface buoy, and surface buoy will send it to the us. So then we will say it is tsunami has come. There are about 7 tsunami buoys which are available in the ocean, available in Indian seas for monitoring and then warning us. This is how the tide level, because the tsunami was measured only variations of the tide, and if you see, this is a signal, it is a tsunami. And then, of course, once the tsunami comes, it actually goes to the rapid mode, and for about 3 to 6 hours, depending upon the number of pulses which come, and then afterward it actually goes back to the normal mode. So these are the two things actually it has events it has connected. In the world, there are very, very big buoys are there. These are 10-meter buoys, which actually 12-meter buoy, which Americans use it. So you can practically sit on that. And then it has a generator to run that. They have a huge instrumentation on these buoys. And then looks like actually a boat. This is called nomad buoy. This is used to basically North Sea, where the season is very, very rough and you have huge cyclones. There is a Pirata buoy as Atlas buoy. It's basically used for doing the measurements in the equatorial, because equatorial is very, very important, where actual all the energy from the sun is coming at the equator. So there are huge networks in all the three major oceans, like Pacific, Atlantic, and Indian. This is basically maintained by Americans. NIOT is actually partner with them for maintaining this network. Then there are different buoys are available for different new tech phase. I will tell you. These are called spar buoys. These are basically vertically stabilized buoys. This is basically used for doing the wave measurements. So when you come to the real-time data transfer, there are actually GSM and GPRS. All of you must be very much aware of that. So if any system is very close to the land, probably we use one of this technology. And then if a little bit far, we use a Immersat and Iridium. Immersat and Iridium is both a satellite space, and Immersat actually is a geostationary based communication system, and the Iridium is a polar orbiting satellite. So it actually power consumption is much lower in the Iridium. And now VSAT is used when there is a normally a communication with the remote station like Andaman. Previously, there is no internet available, network was not there. So we were using continuously VSAT for uplinking the data. Now, of course, they are also having a cable now. So the data is coming through cable. This then new topic actually, like Madam said, what is the areas which people can contribute. Actually, the new areas, this is actually environmental voice is actually picking up in the world. There are no sensor technology available in this area. And then I personally feel colleges have actually better capability to create new sensors, and because you have a fundamentals are much better than the institutions like us. So their sensor technology should be compact, reliable, endurance should be very high, it should have a low power, and multi-band sensors are actually the need of the others. These are the sensors. If you see, I picked up one for you. See, if you see this, these are the optical based sensors, and it has a small brush to clean that, because, well, like I said, they're going to be biofouling is going to happen on all these optical sensors over the period when they're deployed. So these brushes actually clean up after doing the before doing the measurements. They are small, tiny brushes, so to clean them. These are we call antifouling wiper system. These are DO, chlorophyll, turbidity, and nitrates, phosphorus, silicates. You name it, there are sensors available today for doing all these measurements. Then you have a temperature sensors and conductivity. These are simple sensors actually used for the variation of the material designs. And then depth is hydrostatic pressure. PAR is optical sensors, what we spoke. Then pH and ORP. These are all different sensors. Actually, nothing is made in India. And one new area which is actually coming up is using the not only these are basically optical things. People are started using the lasers to do these measurements. I remember I met a person in CSIO Chandigarh. He was talking about using the laser one sensor to do all the measurements in the ocean parameters. In fact, he gave me for demo for a few of them. But the only problem comes is actually the technology to move from the lab to the ocean is actually it is taking time. Then we have a sensors which do the measurements for the currents. These are called actually current profilers. It has a acoustic beams 1, 2, 3, which are looking up the top. See, these oceans actually have a lot of living organisms, which they really don't have a legs or this thing. They just drift along with the currents. So they call like a phytoplankton and zooplanktons and all. So what do we do normally is the currents measurement is we actually track the movement of those things. So the reflection from that is actually measured, and then you actually say, okay, this is how much is the current of the ocean. Then we have a problem with the biofouling. If you see this is something you have a growth, but one of the way to prevent this is there are a lot of anti-fouling paints are available, but some of them are highly toxic, so you cannot use. Some way of actually reducing this anti-fouling problem is using the copper sheet on the top of the sensor. So with that, actually, normally they don't form on the copper. This is one of the expert I thought I'll pick it up one sensor actually to show how it works. It's basically meant for fluorescence. Fluorescence is actually there are different fluorescents out there. One of them is a chlorophyll. In the chlorophyll itself, there are different type of chlorophylls out there. This basically what happens is you send a signal optical beam of 460 nanometers. It absorbs that energy and then give you back at 685 nanometers. So you send it at a blue and then it gives you back at some other wavelength, I think red it is. So then the intensity of that actually you measure and say what is the quantity of the chlorophyll is available. So with this way actually we measure the why chlorophyll is very important. Chlorophyll is basically important. It's actually primary food for the tiny fishes. So there's the start of the food chain. Then there are a lot of other technology voices out there. We saw the open ocean voice which NIOT uses, and there are very near monitoring near shore voice out there for the coastal monitoring. Yeah, this is a platform actually. This is a vertical profiling. This is very important. So normally what it's done in the thing is, suppose you want, this is the water column you have. You wanted to measure at every 10 meters. Practically, we keep a sensor every 10 meters to do the measurement. But the new technology is actually trying to move the sensors up and down. This is basically you have a small winch here, and then your multi-parameter sensor is connected into this, and then you have anchored the buoy. So what happens is because of the winch, the sensor moves up and down. Suppose you wanted to measure every 6 hours. So in the sixth hour, it actually continuously slowly moves out, depending upon the sensor. What do you call it? Is time. Suppose it has actually have a reaction time for about a few minutes. Some of the parameters actually they take a lot of time. So it actually moves every location. What suppose I want every 10 meters. So it moves 10 meters and stays there for 1 minute and then do the measurement. And every 10 meters like that it moves. So with that, with one buoy and one sensor, probably you can do the profile the whole water column. There are different technologies have come up actually doing the vertical profiling because the sensors are very expensive. So we should able to use optimally all these resources. So these are things which are used for the lakes, those basically because the lakes are also huge monitoring goes on. So where this small boy, this system is there on the lake, you have now some sort of a jetty. So you connect to the jetty and connect to the winch, and then it can move up and down. This is how it looks like, the data. You can see the variation depending upon the time. some of the pictures of how we maintain it. The new tech is coming actually is a hub tech detection system. This is basically there are a lot of species which are not actually good for human beings. So we should be able to monitor those and give the alarm, because like somebody is going for swimming, when they know this, when this algae comes, so then you can have a skin diseases. So wherever there's normally beaches where people already normally go, these type of hub detection systems are installed to monitor and give the warning. These algal blooms, you measure these parameters: temperature, light, nutrients, and other parameters. See, there are so many systems are available. We don't do in India. We actually have some of them on the deep sea, on the place. I think off Cochin, we have one boy actually does this measurement. But in India, we don't have this measurements done routinely. Yeah, this is very going to be important, which is going to come in future. This is how any measurements you put it up. You need to have some sort of a user interface to give you nice presentation of the data. Not only storing, the person actually doing the monitoring need to have a nice way of actually seeing the data. These are examples how this data looks like. That's all. Any questions I take?
Sir, good evening, sir.
Yeah.
Very nice presentation, very informative. Thank you, sir. I have a question to you, sir.
Yeah.
You have explained about the tsunami and the devices which we are using to find out the precautionary measures for tsunami. That is good. My question is, what is marine infiltration? Is it related to the tsunami aspect? If so, is there any devices available to measure the marine infiltration? Could you please, sir?
Infiltration, probably you're talking about the species. This is actually last part I have shown is, I think, something related to this algal bloom. Algal bloom basically has come actually, some of the species they form when the nutrients actually come up in the ocean. See, if you take it to the ocean, the subsurface water is actually huge resource for nutrients. So there's something called upwelling happens in the ocean. Upwelling happens just because, like if you take it in the Kerala coast, just before the monsoon, lot of upwelling happens. Means the subsurface water actually comes up like some sort of stream. So when the suddenly nutrients go up, you have actually some of the species which are growing very, very fast. You call it red tide, blue, and if you look at actually some of the pictures available in the internet, the beaches look blue actually in the night. It looks beautiful, but it is dangerous. It's algal bloom of the species which are not so friendly to our to human beings. So whenever these things are there, that's I thought is intervention. For that, there are actually systems available. And then in the world, most of the places we know where this upwelling is there. So wherever the upwelling is there, actually you have these type of measurements systems to put it to do the warning. Tsunami is basically actually is some sort of a variation of the water level that is happens because of the seismic or earthquake, seismic event or earthquake. When the displacement of mass is there, or some sort of meteorite falls, or you have some sort of volcanic eruption underwater. All the three places, what happens is actually you have a force created to move the water. So the energy which is created in the ocean actually moves. The energy cannot stay in one place, so they actually travels. So that is the time actually even the small variations in the deep sea, that becomes a huge variations in the when it comes to the land. So you will find a lot of big waves. So I actually given a lot of lectures on tsunami in Sairam. So I thought all of you must have a little tired of that. So I removed all those slides in this presentation.
Thank you, sir. Thank you for your explanation.
Students
Thank
are
you.
new students, sir.
Students are new. I thought, okay,
Yeah,
I'll
remember,
give
sir.
you- but teachers are old, so you should not feel I'm talking the same thing again and again.
Every time students are new students. So
That will be more interesting. Actually, one topic there are about 30 to 40 slides are there in detail. Yeah. Any other questions?
any other questions, students? Any questions from staff members? Those who are interested to take up this topic as a research. Sir, how about the oceanic research activities, sir? Is it very tough or easy, sir, or
No,
any extra skill set is necessary to proceed research in this domain, sir? Oceanic domain?
no,
Because
there are a lot of areas which you people actually can take it up. And only problem comes only for actually when you wanted to prove the systems into the water, it's little difficult because the activity is little you need a ship or some other place to do this all these things. Otherwise, technology wise is for prototype, yes, not difficult according to me. But working system it takes time. Yeah,
the complete system.
yeah. Working system on this marine is little tough. Yeah.
Is there any optical related research work is going on as of now, sir?
In IoT, nothing is there. Actually, there's one group working in SRM, I think. They have done a lot of equipments. There's one lady called Uma Kumari was there.
Okay.
She was actually came to NIOT to do the validation of the salinity and the pressure sensor what she developed using the optical methods.
Okay.
So I was actually encouraging her to do the means from laboratory testing to the actual field work because that is a very difficult is there.
Yeah,
So
definitely.
yeah, I think she left the SRM, so that work has stopped. But it's like that actually. According to me, the optics are going to be the future for the ocean measurements. I see myself actually a lot of people actually attempting to do that because what is happening is most of the traditional sensors what we are using it like salinity and temperature. There's a limitations are coming in as far as the materials is concerned. You cannot have any salinity measurement sensor which is actually 0.001 accuracy, not more than that. But when you come to the optics, I've seen actually you can go up to the fourth or fifth decimal also, because the now the everybody started doing the measurement very deep in the ocean, like 4,000 meters and all, where the variations is going to be very minimal. So if you want to do the measurement, really what is happening there, you need to have some sort of measuring system which can do the measurement variations very tiny measurements. So I thought optic is going to be future for measurements.
So if any student is asking, we can encourage them to continue in this field.
Yeah.
Optical field. Okay. Okay, sir. Thank you, sir. Thank you. Any questions from the participants? Can free to ask.
Sir, I'm Priya from EC department, sir.
Hello, sir.
Yeah, please.
Yeah.
Sir,
Yeah.
do you encourage any research activities? Like I heard that you have some simulations there, underwater, under ocean simulations.
We have a lot of tools, ma'am.
Whether the tools are free or freely available, or we have to get it.
It depends actually. If you want, if you content work, because there will be about 5-6 heads are there like me. Okay. Now I'm handling two my ocean electronics as well as the data void. There are a lot of facilities are there. If you people wanted to come and work, I think people will encourage. That should not be a big problem. Yeah.
I think with prior permission, those data need to be used.
Data we can give you. Actually, the not much problem actually, because NIOT is really when it comes to the sharing, we are very open. And simulation system, we have a lot of softwares. So many. Actually, I handle computers also. We have few, I think 60 or 75 licensed softwares with us. Some of them actually, the renewal is 1 crore, especially the wave modeling softwares. So there are a lot of simulation tools available, and then people keep developing and then using it. So it depends on actually the person whom you are interacting. You will have a lot of access to all this information.
Okay.
Okay, sir.
Thank you, sir. Any questions? So if no questions, okay. Sweta?
Yes, ma'am.
Aditya?
Participants,
Ma'am, can I start, ma'am?
Yeah, okay. Formal vote of thanks.
Good afternoon, everyone. It is such an honor for me to get the opportunity to propose the vote of thanks on this memorable occasion. First of all, my sincere thanks to Almighty God for making today's event a grand success. I extend my gratitude to Honorable Chief Guest Dr. Tata Sudhakar, Scientist, National Institute of Ocean Technology, to take out time for his busy schedule to grace the event. Thank you, sir. And I express very heartfelt thanks to CEO Sir Sri Sai Prakash Leomuthu, and I express heartfelt thanks to Dr. Purkumaran Sir, HOD Dean Academics, Dr. J. Raja, for the valuable support towards their occasion. I must thank the organizing team and volunteers for working hard for the past few days to making this event successful. Last but not least, thank you everyone once again for making this event a great success. Thank you.